You hear about it all the time, right? The incredible, almost unbelievable power of AI. But here's the puzzle. When you take a bunch of these super smart AI agents and put them together on a team to solve a complex problem, they often fail. And not just fail, they failed spectacularly. So what is going on here? Why do even the smartest AI teams seem to just fall apart?
Well, it turns out the great novelist Leo Tolstoy might have actually hit the nail on the head over 100 years ago. His idea was that success is straightforward, but failure, oh, failure is messy, complex, with 1,000 different potential causes. And this is a perfect way to think about AI teams.
And if you look at the actual data from a recent study, the numbers are pretty shocking. For AI systems like ChatDev and MetaGPT, you're looking at a failure rate of over 60%. And for another one, AppWorld, it's a whopping 86.7%. It seems that in the world of AI agents, just like in Tolstoy's world, most families are, in fact, very unhappy. Okay, so what are we even talking about here? Let's quickly define this. A multi-agent system, or MAS, is basically a team of specialized AIs that are all designed to work together. You can literally think of it like a software company in a box. You've got a CEO agent, a programmer agent, a tester agent, all collaborating to build something. They're being tested for everything from complex software engineering to brand new scientific discovery.
So that's the big question, right? If these systems are designed to be so powerful and handle all this complexity, why are the results so often, well, a letdown? What is actually going wrong inside these digital teams?
To get to the bottom of this, we're going straight to the source. For this explainer, we're diving deep into a groundbreaking, first-of-its-kind paper from a research team at UC Berkeley. They decided to systematically investigate this exact problem. They didn't just guess. They meticulously analyzed hundreds of AI team interactions to pinpoint exactly where things go off the rails. And what they created is pretty incredible. It's essentially a blueprint for failure. They call it the MAST taxonomy. And the best way to think about it is like a diagnostic manual for AI, a systematic way to identify and categorize all the different ways an AI team can fail. So MAST, it stands for Multi-Agent System Failure Taxonomy. And what makes it so important is that this isn't just some theory they cooked up. It's what's called empirically grounded, meaning they built it by watching over 200 real-world tasks and documenting every single time these AI teams actually failed. It's all based on hard data. Okay, so here's how it works. The MAST framework takes all those unique, unhappy failures and neatly organizes them into three main buckets. First, you've got specification issues. That's all about the initial setup and design. Second is interagent misalignment, which is about teamwork and coordination. And third is task verification, which is basically quality control. All right, let's put on our lab coats and act like doctors for a minute. We're going to look at the patient's chart, the data, and diagnose these three major types of breakdowns one by one.
We're going to start with the single biggest category of failures, specification issues. These are problems that are basically baked into the system from the very beginning. They're all about flawed instructions and a poor initial design.
And get this. This is a massive piece of the puzzle. The researchers found that almost 42%, that's nearly half of all failures, fall into this category. The problem often starts before the AI agents have even written a single line of code. And check out this example from the paper. It's just perfect. An AI team was asked to build a standard daily Wordle game. Pretty clear, right? But it created a game with a fixed word list that never changed. The system completely missed the inference that standard and daily meant the word should change each day. This shows it's not just about the AI being bad at following instructions. It's a deeper systemic failure to understand a totally reasonable request. Now for our second category, which is where things get really interesting. This is all about bad teamwork. It's where the individual AI agents just fail to communicate, coordinate, and basically get on the same page. And this is another huge one, right behind the first, making up nearly 37% of all failures. This is the classic failure to communicate that we see in human teams, and it is a massive problem for AI teams too. The individual agents might be brilliant, but they're just not working together. Okay, this example of information withholding is gonna blow your mind. You have a supervisor agent trying to log into a system. It gives the login details to a phone agent. The phone agent gets an invalid credentials error, and it knows the system requires a phone number, not an email. But, and this is the critical mistake, it never tells the supervisor. It just withholds the key piece of info, so the supervisor keeps trying and failing. It's a total breakdown of the communication protocol. And that brings us to our third and final major category, task verification. This is all about quality control. This is what happens when the AI team finishes the job, but fails to properly check if the work is actually correct. Now, while it's smaller, this still accounts for over 21% of failures. This is supposed to be the last line of defense, and it's breaking down more than 1/5 of the time. The system confidently says, "I'm done," but it's wrong. The paper gives this perfect example. An AI team built a chess program. The tester agent ran its checks and gave it a green light. It passed verification. But when a human actually tried to play the game, they found it would accept illegal moves. Why? Because the AI tester was only doing a superficial check, like making sure the code ran without crashing, not checking if the actual rules of chess were being followed. So all this talk about bad checks leads you to wonder, right? If the final step is so often flawed, could we just fix these systems by building a better verifier, a smarter referee? Well, the research points to something they call the verification gap. On one side, you have the easy, superficial checks most systems do, like, does the code compile? Are there any typos? But on the other side, you have deep correctness. Is the game logic actually valid? Is the math correct? And there's a huge gap between the two. So the researchers actually put this to the test. They took the chat dev system and they bolted on a much better high-level verification step. And the result? The success rate jumped by an absolute 15.6%. That's a huge improvement. So yeah, a better referee definitely helps. A lot. But, and this is so important, the paper argues that this is not a silver bullet. A better verifier is just the last line of defense. It's kind of like having a world-class goalie on a soccer team that has no defenders. Sure, they'll make some amazing saves, but they can't possibly fix a fundamentally broken process that's letting the other team shoot all day long. So after all this analysis, what's the big takeaway? If the answer isn't just make the AI smarter or build a better referee, then what is the real fix? And the paper's conclusion just nails it with this quote. It says that real success isn't just about having sophisticated individuals. You can have a team full of geniuses, but if the organization itself, the structure, the communication lines, the workflow is flawed, the team can still fail catastrophically. And that really leaves us with a final provocative question for the entire field of AI. As we build these incredible new technologies, is our focus in the right place? The challenge isn't just about creating brilliant individual models. The real and much harder challenge is designing truly intelligent organizations for them to work in. Are we just building smarter employees, or are we finally learning how to build the smart companies of tomorrow? The answer to that is going to decide everything.